Hey, William, how's it going? Are you ready for the interview?
Everything's going fine. How about you?
I'm doing great. I'm excited to get started.
Yes, I'm excited as well. Can't wait for this.
Okay, so we're going to have roughly 45 minutes. We have a Google Doc. You have your own drawing app that you are sharing with me so I can see your screen, so I can see what you're drawing.
OneNote.
And OneNote, yeah. Let's begin. I'm going to put 45 minutes on the clock starting now, okay?
Okay.
All right. So I want you to imagine that you are an airline. So you support, flying from airport to airport, and you've got a list of airports where your airline is available. And so I'm actually going to be giving you, as an input to this function that you're going to have to write, a list of airports. I'll copy it in the doc here. These airports are going to be these three-letter codes. You might be familiar with them. Like, this is how this is done in real life. So, BUD is like Budapest Airport, LGA is LaGuardia Airport, and so on and so forth. So these are all the airports that you've got at your disposal for your airline. And then I'm also going to give you a list of airport routes or airport connections. So for the purpose of this question, I'm going to use the words routes and connections kind of interchangeably.
Okay.
They're going to look like this. So they're going to be pairs. It's going to be like one list of lists of length 2, where you've got two airports in the lists.
Okay.
And what this represents is it means that your airline has a one-way flight from the first airport to the second airport.
One way.
So for instance here, one way. So you can fly with your airline from DSM to ORD. You can fly from SIN to CDG, etc. Okay?
Yeah.
Now, you're the kind of airline that really wants to support its travelers. You want to make sure that your travelers can travel the world, experience all of the airports that you have, connections to or flights to. And you have one airport in particular that's really popular. We're going to call this the starting airport. Maybe it's like your headquarters or something like that. So I'll put it here. This is going to be the third input to your function. And here, this starting airport is going to be LGA, LaGuardia, which is in our list of airports. You want to make sure that any traveler who wants to travel to one of these airports, starting at LaGuardia, can do that. You want them to be able to reach any airport in your list of airports, starting at LaGuardia.
Okay.
Now, the thing is, as you might notice in the routes, LaGuardia isn't necessarily connected to every airport. In fact, I don't think LaGuardia has any outbound flights here.
Yeah, it doesn't.
It doesn't, yeah. So what you're going to have to do is you're going to have to write a function that is, or devise an algorithm that is going to determine the minimum number of routes or connections, so one-way flights, that you have to basically allow as your airline to enable any passenger to go from LaGuardia to any other airport. Now, the one caveat is that it doesn't have to be that the passenger can you still hear me? Can you still hear me?
Oh, your voice got cut off.
Okay, can you hear me now?
Yeah, I can.
Okay, perfect. So, like I was saying, you want to make sure you want to allow all of your passengers to be able to go from LaGuardia to any other airport. Now, the only caveat is that they don't have to be able to go directly from LaGuardia to another airport. It's okay if they fly through other airports. Does that make sense?
Any number of airports?
Yeah. So, for example, like imagine you could go from LaGuardia to SAN down here in the routes. That would mean that you could also go from LaGuardia to EYW because you could first go through SAN. Does that make sense?
Yes. So the passengers don't care about having like 5 transfer flights?
They don't care about having 5 transfer flights. All they care about is being able to reach the destination airports. But you have to, you're working on behalf of the airline, so you want to minimize the number of connections or routes that your airline is going to have to support so that every passenger can go from the starting airport to all of the other airports. And it turns out, just to give you the answer for this particular example here, the answer would be 3. So I'll write it down. We'll put answer 3. The reason it's 3 is because if you connect, basically, like you can add 3 connections that are going to allow your users or your passengers to go from LaGuardia to any other airport.
Okay. Do you know which 3 you need to add?
Yes. So, for example, you would add 1 connection from LaGuardia to Tel Aviv, TLV, and the reason is because that opens up a lot of flights, right? Then you would add 1 to either SFO or maybe SAN here, and then finally you would add 1 to EWR.
Okay. Okay, so that's the entire problem, right?
That is the entire problem, yep.
Oh, okay. So first off, we have a list of airports and a list of one-way connections. So you can basically formulate this entire problem as you can basically formulate this entire structure as a directed graph.
Okay.
Okay, so now, do you know about strongly connected components?
Remind me or educate me.
Okay, so imagine if we have a directed graph. So
okay.
Maybe it looks like this. And then in this graph, we have, you might notice that, actually, I'll just do this. You might notice that there are these components there are these group of nodes, okay, such that start from any node in the group, you can travel to any other node in the group. So for example, if you start at this node over here, then by following the edges in here, you can also travel to all 3 other nodes. And the same is true if you start at the other 3 nodes. You can always reach the 4 nodes. So after you find these, first of all, these strongly connected components will be disjoint from each other. So because if you imagine that if we have 2 strongly connected components where one node is part of both, we know by the definition that we can travel from, let's number these 1, 2, and 3. You know by definition that we can travel from 1 to 2 because they're in the same component, and then you can travel from 2 to 3 because they're in the same component. So in fact, we can also travel from 1 to 3 and 3 to 1 as well. So in fact, if these 2 groups of nodes can all travel to each other, then this entire group of 5 nodes is just one strongly connected component. So so what I just showed is that these components are disjoint. So is that part clear?
Yep, that makes sense.
Okay, so after we find all of the, so notice that each node will be part of exactly one component. So because single nodes will just be their own component. So each node will have its own component. And then after we do this, we'll compress all of the components into nodes. So what I mean by this is this original directed graph here will become a new graph like this. We're just basically taking the components and we're just basically taking the big circles and then like making them into the new nodes.
Sure.
Okay, so, and then in this new graph over here, the compressed graph, what this achieves is that we'll get an acyclic graph. And that's true because, for example, if we had a cycle like this, so if these three formed a cycle, then what would happen is that these three would actually be part of the same component. So it's impossible for the new graph to have any cycles.
Right. That makes sense.
Okay. So now we get to like our. Oh, by the way, like we can just work with the new graph and completely ignore the original graph, because as long as we can reach some node in a component, we can reach all nodes inside the component. So,
Sure.
Yeah. Okay. So, and then let's say that I'll just create a new like compressed graph. So if our new compressed graph looks like this, and maybe I'll just draw a few more, and then we have our starting node, which can be basically, let's say the starting node is over here.
Yeah, that's fine.
We'll basically add new directed edges from S to other nodes. So for example, we could do this, but then adding this edge doesn't help because like this node was already reachable from S already in the beginning.
Sure.
Okay, so now the nodes which aren't reachable from S are these nodes over here with an in degree of 0. So they don't have any nodes pointing towards them. So it's impossible for S to reach these nodes, to reach these components.
Okay.
Okay, so it means that we need to like cover these nodes. We need to like add edges so that any person starting from S can travel to these nodes, right?
Yep.
Okay, so the only way we can do that is if we add an edge from somewhere connecting to like this node over here, and we need to do the same thing for this as well. And then notice that if these two nodes with in degree 0 are reachable from S, then that means that all other nodes will also be reachable from S as well. As long as we cover the nodes with in degree 0, then we'll be fine.
And just to clarify, William, when you say in degree 0 or n degree 0, you're talking about like inbound edges, right?
Yeah, like in degree is inbound edges, and then out degree is outbound edges.
Yeah. Okay.
So we know that we must at least add an incoming edge to each of these two nodes in order to like satisfy the problem. And one way you can do so is just to connect it to S. So we'll just connect them like this. And then after we connect a new edge from S to each node with in degree 0, we will be able to like all nodes will be able to be reached from S.
Yeah. Okay,
so the answer for the problem will just be the number of nodes with an in degree of 0 which are not S. So in this case, it's just 2. And so the entire algorithm here is, so first, I'm on the Google Docs right now, by the way. So
yep.
First thing we do is we'll process the input. So we'll make the strings into some more usable form, I guess. So
okay.
Then we'll find the strongly connected components. Okay, and then next step is to compress the graph based on components. And then last step is find number of nodes with in degree equals 0, which are not S in the new graph. And then that'll be our answer.
And just, William, for the number, that last step, the number of in degree equals 0, which are not S in the new graph, is it not possible to have two nodes with in degree 0 that then connect the same node? It is possible, but those two nodes would still have in degree 0, so you would still need to reach them. So actually, disregard what I just said.
Yeah, so we know that like we must connect these type of nodes, and then it happens that once we connect these type of nodes, all nodes will be reachable. So we establish the lower bound and the upper bound for the answer to be this number, the number of nodes with an in degree of 0 which are not S.
Yeah.
All right, so Should I?
So if you want, why don't you, before you jump into the code, why don't you just very briefly walk me through like how you are going to conceptually do these 4 steps?
Okay, so processing the input, I guess. So first, I'll just go through the list of airports and then assign each string an ID number for the airport starting from 0. So
Okay.
0, 1, and then what I'll do is I'll create an adjacency list to represent the graph. So for each of these, I'll have a map which stores the string and an integer, and then this will be the map which converts from the name of the airport into the ID of the airport. And then
Sure, sounds good.
I'll go through the list of routes, and then for each route, I'll convert the name into the ID, and then so first, what I'll use to store the graph is I'll use an adjacency list. So basically, a vector is just a list, and then I'll have, so for each of the n nodes, I'll store a list of which nodes it can reach.
Yep.
Example, let's say DSM, if DSM is 0 and ORD is 1, then what I'll do is I'll add the value 1 into adjacent 0. Is that?
Yep.
Okay.
Totally, yep.
Okay, so now I created the adjacency list of the entire graph. And yeah, that's basically what I wanted to do in the input.
Yep, sounds good.
Based on the adjacency list, I will find the strongly connected components. So this is the more I guess this is the more interesting part of the solution. So there are actually algorithms which do this for you. I think it's called Korsaju's algorithm, and it'll basically it'll give you the strongly connected components of a graph in O of n plus m time, where n is the number of nodes or the number of airports in our case, and m is the number of edges or the number of routes in our case.
Sure.
So should I explain this algorithm? Like, I don't exactly know how to, don't really exactly know how to explain it. I just kind of know it.
If you want for now, let's skip it, and once you get into the implementation details, we'll talk about it there. But the idea is here, you're applying this algorithm to get all those strongly connecting components. And I'm assuming is the idea that your output there will be another adjacency list, but for just these new connected component nodes, or what?
I guess the output will be, so for each component, they'll choose a representative node of the component arbitrarily. So maybe these are the representative nodes of each component. And then what we'll do is basically have this array called who of u. Basically, who of u will return the node, which is the representative node of its component. So for example,
sure. Okay.
I call it, if I want the who value of this node, then it'll return this node because it's the representative node of its component. And then
gotcha.
Yeah, okay. So this algorithm should return it should create this who. I guess I'll just write a function for this. So actually, I'll just not care about capitalization.
Yeah, don't worry about that.
Just call it solve because I don't know what to call it, and then I have a list of airports. So be a list of string. Then I also have a list of strings, which will be the routes. And lastly, I have the starting airport, which is a string.
Yep.
Okay, and then so first step, I go through the list of airports and assign each string and ID number. So to start with, I'll just find n, which is just size of list of airports, and then I also have this map to convert from each string of the airport to its ID. Then I just go through each of the airports, and then I'll set the string. I'll put an entry in the map with the string as the key and I as the value, and I will be the ID of the airport.
Okay.
And then I create this. Actually, I'll just do this kind of like in competitive programming. So I'll have a maximum value of n. I'll just make it something like this, and then I will And then I need to declare this adjacency array on the outside with the max value of n. So this part is still okay. And then I go through the routes. Actually, I'll just do this. So for each edge, I'll just add it into the adjacency list. So the starting node will basically I'll basically use my map to find the ID of the starting node, which is the first node of this list. And then I'll find the ID of the second node. And this will basically add the edge.
Yep.
And then the second part is running the strongly connected components algorithm. So for this, I'll need it gives me a who array. So I'll declare this as well. And then for the algorithm, for this algorithm, I also need a reversed adjacency list. So I'll call it RJ. And then I also need what is it? I need a stack for this. Okay, and then in the start of the algorithm, I'll create the reverse adjacency list. So basically, for each edge in the adjacency list, I'll just add it to the reverse adjacency list. I'll just swap I and j to make it reversed.
Right. Okay.
Okay, and then the algorithm consists of two parts. The first part is and I also need a Boolean array to store if I visited a node or not for the DFS that I'm going to run.
Okay.
Okay, so if this node is not visited, then I'll run DFS on it. So let me write the code for DFS1. So when I visit this node, I should set it to visited, and then what I'll do is I'll try to visit other nodes from this node. So for each other node in the adjacency list, if it's not visited already, then I'll visit it. And lastly, I need to add this node into a stack. Okay, so that's the first DFS function.
You're adding the node that you are currently doing DFS on in the stack?
Yeah, after I visit all other nodes.
Okay.
And then the second part, I basically go through the stack starting from the top of the stack. So while like the stack is not empty, look at the top of the stack, and then I'll remove it. Okay, and then so what I'm going to do here is actually I'll just create a new array called viz2. So this will act the same. This will have the same function as the first viz array, but then it'll be for DFS2.
Okay.
And then if it's not visited, then we'll visit it like this. And then now, remember that we need to find the who array. Like this node u here will be the representative node of the entire component. So what DFS2 will do is DFS2 will go through all nodes in u's component, and it'll set those nodes to it'll set the representative nodes of all those nodes in the component. So
to you.
Yeah. Did you say something?
No. I said I just confirmed what you said. Yeah, to you.
Okay, great. So be the representative. So first, since we visited, we set it to visited, and then we set the who array. So we set it to the representative. And then and at this time in DFS2, we work with the reversed adjacency list. So we do pretty much the same thing. And then if v is not visited, then we'll visit it. And this time we go to node v, but then the representative is still the same. So we call DFS2 v and rep.
Is the reason that you are going through the reversed adjacency list here? I guess what is that reason?
The reason is with how this algorithm for finding the components works. So I haven't really thought much about why this algorithm does this. But if you want me to, then I can try to find a few examples.
Let's assume for now that I trust that it works. Just interesting, and I'm sure that there's a piece of logic that makes everything click together. But okay, let's assume that it works.
Okay, so now after this entire loop of 2 DFS, I basically found the who array for each. for each node. So now, for this problem, we can just ignore the new adjacency list. We only need to work with we only want the degree of all the nodes. So
Yep.
I'll create this array I'll just create this degree array, and then let's see. So yeah, we go through the edges. And then what we do is we check that these two are in different components, and if they are, then we add an edge from who of I to who of j. So the in degree of who of j increases by 1. So this will give us the in degree of all of the in degrees of all the nodes in the new graph.
Yeah, because if they don't have the same representative node, then the one that we are pointing to has an in degree. Okay. Yeah.
And then last step, we found the degree array. Now we just count the number of nodes, number of components with a 0 in degree and don't contain s. Okay, so this will be our answer. So we go through each of the nodes and first check that it's a representative node, so who of I should be itself. And then you also check that it has a degree of 0. So now we make sure that it doesn't contain s. So as long as I is not equal to the who of the ID of s, and the who of ID of s, I'll just use the map to find the ID, so it's starting airport. Okay, so if all these three conditions are true, then that means we need to add an edge from the starting airport into this node. So we add 1 to the answer. And
can you repeat why you're doing the first condition, the who of I equals I?
Oh, okay, so I'm basically iterating through all nodes in the original graph, like from 0 to n-1. But then what I want to do actually is to iterate through all nodes in the new graph.
Oh, the condensed graph.
Yeah, the condensed graph. So those so in order to iterate through only the nodes in the condensed graph, I make sure that the node it's representative in its own component, since each component has exactly 1 representative. So each component will be checked through exactly once.
Gotcha, I see. So this condition sort of like cleverly ensures that you're only going through those representative nodes.
Yes.
Gotcha. Okay.
Okay.
Cool. So it looks like you're done here, right?
Yeah, I'm pretty sure it is.
Okay, so before we've got like a couple minutes left on the clock, which is like kind of perfect timing. Let's see if we can just if you can walk me through all of the various like code blocks and their complexity analysis.
Oh, okay. So, yeah, I forgot to do that. Okay, so the first part, and by the way, for map, again, C++ map, it's basically a binary search tree. Its operations are like overlog, and like if I want to improve the operations to constant time, I could use a hash map using an ordered. But I didn't like really care about this, since it doesn't really matter to making the solution correct. Anyway, so in order to improve the complexity, I'll just use an ordered map here. Okay, so the first part, this loop